Hello, class. This is a week 7 Monday lecture. The previous video had some problems in the recording, and so I'm going to redo this lecture. I'll follow this up with a second lecture that'll finish up Chapter 5. So we're going to discuss rigid body equilibrium, which is the most fundamental chapter in statics. It's one of the easiest chapters, provided you learn how to construct a free body diagram. But it is probably the most critical, most fundamental chapter in all of statics, which leads into the second course, strength of materials. So I will So we're looking at Chapter 5, equilibrium of a rigid body. And I start off with a general shape, a rectangular shape. It could represent any structural shape. This is just for illustration purposes. I've applied several loads to this rigid body. F1, F2, F3, F4, F5, F6, as many as we need to have. And I've at random selected a certain point, and we'll call it 0, O, in this rigid body. So what equilibrium means is the following. If we sum forces in the F direction, we get a force resultant, and that force resultant must be equal to 0. We sum moments about this point 0, which is going to give us the moment resultant about that point 0, which means that it must be equal to 0. So basically, sum of forces equals 0, sum of the moments about a point, any point in your structure, equal to 0. These equations are what we call necessary and sufficient. Again, we've talked about this before, the fact this is rigid body, we neglect deformation. It's negligible in the problems. We know deformation is going to occur, but in these problems, it's going to be negligible. And it's not going to result in any significant error in the calculations that we do. So one of the things that we look at the direction of forces and the moment arms will not change under loading. That's exactly what this means, that we don't have deformations. So these forces aren't going to change under loading. Moment arms aren't going to change. They're going to remain the same. So we neglect any deformations that are going to occur. So we start off talking about equilibrium in 2 dimensions, which is planar equilibrium. And we're going to discuss the free body diagram, which is absolutely mandatory in solving these problems. And I always tell students, and I emphasize this in class, if you can draw the free body diagram, you can solve the problem, because it's just a matter of summing or taking a moment about a point and summing forces in the X and summing forces in the Y direction. That's all there is. The math is easy. However, some of the structures that we look at may be a little bit more complicated than we're used to. And in order to use these equations, moments and forces, we have to be able to reduce this complicated structure in a very simple structure via a free body diagram. And if you can draw the free body diagram, you can solve the problem. Okay, so the first step in solving any problem is to be able to draw the free body diagram, and we'll show you some examples of free body diagrams here in just a few minutes. And this concept of supports is sort of a new concept for us and very, very important. So what I have drawn here is a simple beam. It's supported at point A at the end of this beam. This is, we'll learn this is a pin connection. Over here at B is a roller connection. Okay. The pin A can supply a resistance to translation in any direction. So in general, what you might look at is some reaction that's in any direction. Okay, so there could be a reaction this way, depending upon the loading that we have. But what we do, we're not interested in that single reaction. We want to, in terms of solving the problem, we need the reactions in the X and Y direction. And so a pin A is going to provide a sum of force reaction in the X direction. So it's going to resist translation in the X direction. It will also supply a Y direction resistance. Okay, a reaction in the Y direction that's going to resist translation in the Y direction. If you add those two together, you get a single vector quantity that tells you which direction this thing would actually move if it could move. But what we will simplify, because we're working with planar, is we're looking at X and Y components at pin A. So pin A has two components of reaction. Now the roller B, a roller is free to move in the X direction. Okay, it's going to be able to roll this way. It's going to be able to move this way. So there's no resistance in the X direction. However, this beam can't move in the Y direction with a roller. So a roller has as its reaction component a single force, and it's going to be perpendicular to the surface that it's resting on. And in most cases, the orientation is this way, so it's going to be the Y component. Okay, so the roller B is free to move as a Y component. A pin as an X and a Y component to take a look at. So if we have a beam. I've got a beam. I labeled the support ends A and B. A and B. I applied a force, some angle up here. There's a force. What we're going to do is we want to draw the free body diagram, which means that we separate this beam from its supports and provide the supporting reactions that will keep this basically suspended in space. So what I would do is break this force F into a Y component and an X component. And then I would show my I would call it A sub Y and an A sub X. And then I would have a B sub Y. And the solution would take maybe 2 minutes. Okay, and we'll do some problems on there. It's just a very, very simple solution. So these are simple supports, pin and a roller. We also will be involved with a fixed support. This is a cantilever beam. It's fixed at this end, and we'll see some of the applications of what a fixed support might look like. And again, we apply a force at an angle out here. The support is labeled A. And we know this is going to provide a y component and an x component, so we're going to have a y reaction and an x reaction, okay, which I have here. Also, we recognize that this force would cause a rotation in this cantilever being in this direction, okay, in the clockwise direction. So this moment that it creates out here, because it's a cantilever beam, has to be resisted. Again, we don't want rotation, so it has to be resisted at this support. And so we're going to have a resisting moment. I'll call that M sub A. And it would actually be in the opposite direction in this case, counterclockwise. And so with a fixed support, we actually have three reactions, A sub Y and A sub X, and a moment developed also in a cantilever. Okay. And I think your textbook gives you additional support restraints for different connections. These two above are the most common that we will use. Also, we see a cable and also a link, and I'll show you a couple of problems with those. Cable will always be in tension. A link typically is going to be in compression. And what happens is, suppose that you have a structural component, pen has dried out. Let me get another pen. It's a little bit awkward when you have this platform out here, getting to the other desk. So if we have a structure that might look like this, and we'll do one, there could be a strut support here, put a load out here. The reaction in this strut is a force that's going to be directed along the strut, and in this case it would be a compressive stress going through that. Okay, so simple supports, a pin and a roller, fixed support. We'll see cables and links. I don't know that there may be something else, and we'll figure out what the support looks like, but those are typical what we use in there. So we'll have five, so the equations of equilibrium in planar, 2 dimensions. Typically, a some forces in the x equals 0, some forces in the y, some moments about some point equal to 0. And I will tell you now that there's always a check equation, basically to check your math. So you work a problem on an exam, show you how you can check to see that at least your math is correct. And really, depending on the problem, the whole problem is correct with this check equation that you have. So you can also, instead of these three equations, you could also have sum of forces in the x, sum of moments about A equals 0, and sum of moments about B equal to 0. If you do this, it's important that A and B are not on the same line. Okay, the only time you can do this is if A and B are not on the same line. So for instance, if we had something here, A and B are not on the same line. Okay, so that could be used in that case. You could also have sum of moments about A, sum of moments about B, sum of moments about C. A, B, and C are not on the same line. You can solve the problem without using forces in the X and forces in the Y equal to 0. Almost every problem we're going to deal with, we'll use these three equations: forces X, forces Y, and sum of moments equal to 0. And again, we ignore internal forces. They actually occur in collinear fashion, equal and opposite, cancel each other's out. Newton's third law. We also, several of the problems we'll run into will use weight. Okay, and weight is always considered acting as a single force at the center of gravity. And if the weight is involved, rest assured that the problem will tell you where the center of gravity is located. So our solution model for analysis are idealized representations of actual objects. Free body diagram. That's basically a model that you're creating. So we show the reactions, forces, dimensions. Okay. And what we don't indicate are materials, because of the fact that we don't have any deformations occurring, so the material is relatively insignificant when we do this. And most always in problems and in engineering, we use an extreme condition for design, and we do that using a factor of safety. And the reason for that, there are many reasons for that. We've seen the interstate being reconstructed around roads, okay, I-40 outward past Tinker. And if you're around before the construction started, those bridges along there, basically they were falling apart. Had concrete just dropping out from the bottom of the structure. They had supports underneath, and it's deteriorating. So you have material deterioration over a period of time occurring. You could have steel could be corroded in harsh environments. When you start designing and you're putting loads on a structure. The one that I've encountered most often in my consulting is a change of use. A building could have been built 20, 25, 30 years ago for a specific purpose. Building is sold and a new company moves in, say a manufacturing concern, and they're going to reconfigure this building to suit their needs, which means that there are probably going to be loadings, equipment in there, maybe hanging stuff off of steel beams. And in the design, it didn't account for that. I mean, we didn't know those loads were going to be there. But what we do use are factors of safety. So if you design a load you think it's going to be 1,000 pounds, let's say, and your factor of safety is going to be 2, you design it for 2,000 pounds. And it accounts for deterioration, it accounts for change in use. Okay. The larger the factor of safety, the more unknown that you have. Critical structures have obviously a higher factor of safety. Some of the bridges, support systems, dams, our critical infrastructure. Lived in California for a while, did some work out there near some of the fault lines. Actually, it's basically right on a fault line. Very high factors of safety for hospitals, for infrastructure, simply because of the earthquake possibility. So the unknown factor or change in use factor is important. And a lot of times then in design, the loads that you see have a factor of safety applied. primarily because these structures could be in place for age, and there could be deterioration of the structure, a change in use. Those are the two critical things that might impact what's happening. Okay. So in terms of theory, that's very simply, that's the theory in Chapter 5. The issue is being able to draw your free body diagrams. That's the real issue. And what I would have students try to do is, in classes, try to do the free body diagram. So here, here's a couple of, we're going to do about 3 examples of just the free body diagram. So here's a dump truck. We know the weight of the bed and the load is applied at center of gravity. So we have a weight. We've got dimensions along the bed of the truck. It's lifted by this hydraulic ram, 30 degrees. Okay, so this hydraulic lift controls the position of the bed. We got wheels, obviously, when we're looking at it. This connection here is a pin connection. This bed needs to be free to roll up and down along this axis here. So we're going to consider this a pin connection. The problem is, given the weight acting at G in this position of the bed, 20 degrees, this is 30 degrees with this. We want to know what the pin reactions are and what the load is, the force is in BC. Okay. Looks complicated, it is. But what we do is we use a free body diagram then to simplify it. And once we draw the free body diagram, we should be able to solve the problem. So here's what I would do with the free body diagram. I'm just going to show the bed. And I've got reactions here at A. So I'm going to have an A sub Y, an A sub X at this point. I've got a weight W. This bed is at, couldn't label everything that I have on here. This bed is at 20 degrees. And now I have the hydraulic setup here that's going to operate the bed. Okay. And that's labeled BC. So compression, BC. And this angle down here, BC, is 30 degrees. And I have dimensions now. That are following this angle 30 degrees with the bed. So it's 3 meters and 4 meters. 1.5 there. So it's 3 meters to this, so it's 3 meters this way. And then it's an additional meter. I have to drop all this down here, 1 meter here. Okay. We got all the dimensions given, and the weight will be given also. And the solution, we've got 3 unknowns. So what I'm going to do is take moments about A, and I'm going to solve for BC. Okay, and I can do this a couple of different ways. I can get the X and Y components, and then I can get the X and Y dimensions, okay, the X dimension and so on. And we can solve for BC. And once we have BC, we can solve for A sub X, A sub Y using similar forces. So the key is being able to draw the free body diagram, and you got the solution. Then you can do the solution. Got to work with angles and solve a few of the problems will do that. You've got to make sure you get the dimension in the right direction according to slopes. And let's look at the second problem down here. Again, we have some kind of a structure, a beam that's fitted at a fixed support. Actually, it looks like a pin connection here. So this is a pin connection at A. There is a pulley system with cable attached at B and E. And then we have a weight that it's supporting out here at C, which is going to be a known value. So what we need to do is simplify this and draw the free body diagram. Okay. So what I have to draw this up here. And we also probably have the weight of the beam itself in here that we're looking at. So I have a load, or W, that we have at A. We have an A sub Y, an A sub X. Okay, the cable. There's tension in this cable, and it's the same. It's attached here at E and B. And remember what free body diagram does. It separates the structure from its supports. So we need to separate this beam from its supports at E and F, which is this cable going over a pulley. So what happens is we have a tension in this cable. I'll just call it T over here at point E. And this same tension then is over here at B. So I have this tension also. Let's say we neglect the weight of the beam at this particular point. And then what I'm going to do is dimension this. So this is 2 meters, 2 meters, 1.5 meters. The slope is a 3-4-5 slope. So it's a 3-4-5 slope. And the solution then, once we have this as a free body diagram, is really very, very, very simple take moments about A, we have this W, and then we have T directed straight up, and then we have T again, which is going to be 4/5 of T times its moment arm. And you solve for T, taking moments about A. And then once you have T, some forces in the X to get A sub X, some forces in the Y to get A sub Y. A sub X is equal to the 3/5 component of T, and then A sub Y is equal to the T minus the W plus the 4/5 T that we solved. Okay, and we have the W in here also. So again, we take I'll say it's a complicated structure, but you got to say, well, what are we going to do with this? Construct that free body diagram, and it ends up being a really quite a simple problem to work with. Here's another problem. This is it's like it's some type of a pipe, pipe-like structure. It's propped up in this 90-degree angle. It's in contact at A, in contact with the vertical wall, or at B with the horizontal base. It's in contact A with the vertical wall. It looks like this is another wall system. It's in contact at point C and continues on. And what we want to do is find the reactions at A, B, and C. We know the weight is acting at G, and so we draw the free body diagram. I'm going to definitely draw the shape of the structure. So I think the reaction for this type of a contact is a single reaction that's going to be perpendicular to the surface that it's acting on. So this is B. There's a reaction at A that's going to be perpendicular to that wall. So this is A. And then C is going to be perpendicular at this point. And then we would have a weight W, and we've got the slope is 30. And we would have the dimensions. .75 meters, 0.25 meters, and don't really need this dimension out here. We don't need this dimension across here. So that's your free body diagram for this problem. And again, we just apply some forces in the X and some forces in the Y. This problem, I'm going to work this one in a few minutes. This is a little bit of an unusual problem, and you may see a problem or two like this. First of all, we want to solve for that. No, this is a fixed support here, so you'll have an X and a Y component and a moment component. That's what you're solving for. we need to get the x component and the y component of the force, okay, which is easy. We know the angle is 30 degrees. Okay, so the x component is cosine function 34. The y component is sine function 30 of 4 here. But when we start taking moments, we need the perpendicular distance. So this distance, we know this distance is 1.5 meters. What we need to do then is get this distance out to here. And then when we start looking at this component, we need to get this distance also, which would be, just taking the sines and so cosine functions of here. So in effect, what we do is straighten this out. Okay, this dimension, just straighten this 30-degree incline out. So we're measuring this way, and then we're measuring up the way this is here. Okay, I'll show you that in a problem. I think I'll work this problem in a few minutes, and I'll work this problem also in a few minutes. This is an interesting problem. Again, this is really complicated. This is I may do this in the next lecture. I'm not sure. We know the total weight of the floor crane and the driver. It's 2,500 pounds. It's acting at G, the center of gravity. Okay, so we have center of gravity. Okay, acting for the total weight of this thing. And this crane is lifting a drum, and what we want to know is the largest weight of this drum that can be lifted without causing the crane to overturn when the boom is in this position, okay, at a 30-degree angle. This is a real problem in factories, in warehouses. What's the maximum load that you can have, and trying to figure out what angle, and it could be varying angles, would definitely affect the load that you can do. And you want to keep this crane from tipping. And so if it's going to tip about this point over here, and which means you're going to lift this end up over here, end A. And so the question is, what happens to this structure when you have the tipping occurring? And so what I'm going to do is go ahead and work this problem in the next session. I'm going to work 3 problems in the session, and then that will conclude our lesson for that particular time. I'm going to show you this problem. Do this one problem here. Okay. So just want to show you, and then we'll work the problem. So what I've done this is the problem, and I've got it sketched out like this. And this is how I would do the free body diagram to work the problem. Sometimes you can really simplify it, but I need to show the angles and what we're going to be doing here. Okay. This is 6kN load. I have the 4kN out this way. So I'm going to break this down, this 4kN, into X and Y components. And we see this angle is 30 degrees. And so I've got the X component is 4 cosine of 30 degrees. It's adjacent. The vertical component is opposite the 30, which is going to be sine function. So here's 4 sine of 30 degrees. This distance is 1.5 meters. I need this distance to this load. Again, this is going to be a cosine function of the 30 degrees. Okay, so we're up here. This is the dimension 1.5. Adjacent, so this dimension is 1.5 cosine of 30 degrees here. And this dimension, again, 30 degrees, it's 1.5 is opposite. So this dimension is going to be 1.5 sine of 30 degrees up to this X component that we have. So once you've done all that, I just started as sum of forces in the X equal to 0. Well, we'll put our reactions in. I have an A sub X, A sub Y, and a moment sub A this way, right here. Okay, so A sub X, A sub Y, and a moment sub A. It's a fixed support, so I have my 3 unknowns. Got all my dimensions given. I just sum forces in the X equal to 0. My A sub X. And then the only other X component I have is this 4 cosine of 30 degrees. So A sub X, 4 cosine of 30 degrees equal to 0. A sub X is minus 4 cosine of 30. A sub X is minus 3.46 kN. Okay, again, 3 places. So what does this minus sign mean? Well, it means the direction that I originally chose, A sub X, is incorrect. So I'm not going to go back up here and change it. It gets messy. What I'm going to do is block my answer in and show the direction. Okay, it's directed to the left. This minus sign says my original direction is incorrect. And so I'm going to show the direction directed to the left. I sum forces in the Y. I got a plus A sub Y minus 6 kN. And then this component in the Y direction is minus 4 sine of 30. A sub Y is 8.00 kilonewtons, and it is directed up. I'm going to go ahead and put the direction here since I did here. The direction was correct here, but I'm going to go ahead and show it. Okay, so there's the A sub Y. Sum of forces in the Y. The A sub Y up, minus 6 down, minus 4 sine 30. So A sub Y is 8.00 kilonewtons, and it's directed up. Okay, it ends up being, once we do this, get the force in the X and Y direction, and once we get the distances in the X and Y direction, the solution is very, very simple when we do that. Then I just take moments about A equal to 0. I have my 6 here times its moment arm, which is 1.5. Okay, minus, I have minus 4 sine 30, this force times its moment arm, which is the 1.5, which is 3, plus the 1.5 cosine of 30. Okay. So it's 3 plus 1.5 cosine of 30. And then the other force moment that I have is this one, is the 4 sine or cosine of theta, which is going to be this, and its moment arm is going to be this distance that we have here. So 4 cosine of theta times 1.5 sine theta. Okay, so what I have is this force creating a moment, and this force creating a moment also. Okay, this moment arm for this force, this moment arm for this Y force here. So I got 3 components, and then MA is comes out positive 20.2 kilonewton meters. Okay, and then counterclockwise direction. So I'll follow this up fairly quickly with another lecture, which would be the Wednesday lecture. It won't quite finish up chapter 5. I've got a couple of 3D problems that I want to do in chapter 5, and maybe a couple more of these 2-dimensional problems. But we should finish up in the next lecture, and then we're going to be starting chapter 6 right after that too, which is on structural analysis. So we'll leave this lecture. This was a week 7 Monday lecture, and I'll follow this up with a week 7 Wednesday lecture. We're just going to do a few more problems and introduce the concept of 3D. And then next week we'll finish chapter 5 and then start on chapter 6.